Esse é o nosso trabalho de física e o grupo é composto pela Bel, pela Gabriela, pela Dora e pela Sabrina, e a gente é do segundo ano B.
No trabalho, a gente procurou mostrar a física na medicina diagnóstica, e para isso nós escolhemos 3 vídeos explicativos que falam sobre 3 exames diferentes e como a física se comporta em cada um deles.
The heart of most ultrasound systems is a device called a transducer, which uses an array of piezoelectric crystals. A piezoelectric crystal vibrates when an electric signal is applied, producing high-frequency sound pressure waves, which we call ultrasound. More importantly, this type of crystal can also work in reverse. It can produce electrical signals when it detects high-frequency sound pressure waves. When a transducer directs ultrasound waves into the body, they pass right through the skin and into the internal anatomy. As the waves encounter tissues with different characteristics and densities, they produce echoes that reflect back to the piezoelectric crystal. This happens more than 1,000 times a second. Returning echoes are converted to electric signals, which a computer converts into points of brightness on the image, corresponding to the anatomic position and the strength of the reflecting echoes. A medical transducer contains a large array of crystals, which allow it to make a series of image lines that, together, form a complete image frame, called a sonogram. In addition, all the crystals are repeatedly activated many times in such a way that a complete image frame is formed around 20 times per second, so that real-time motion is displayed in the ultrasound image.
In 1895, a physicist named Wilhelm Röntgen was doing experiments with a cathode tube, a glass container in which a beam of electrons lights up a fluorescent window. He had wrapped cardboard around the tube to keep the fluorescent light from escaping when something peculiar happened. Another screen outside the tube was glowing. In other words, invisible rays had passed through the cardboard. Wilhelm had no idea what those rays were, so he called them X-rays, and his discovery eventually won him a Nobel Prize. Here's what we now know was happening. When high-energy electrons in the cathode tube hit a metal component, they either got slowed down and released extra energy, or kicked off electrons from the atoms they hit, which triggered a reshuffling that, again, released energy. In both cases, the energy was emitted in the form of X-rays, which is a type of electromagnetic radiation with higher energy than visible light and lower energy than gamma rays. X-rays are powerful enough to fly through many kinds of matter as if they are semi-transparent, and they're particularly useful for medical applications because they can make images of organs, like bones, without harming them, although they do have a small chance of causing mutations in reproductive organs and tissues like the thyroid, which is why lead aprons are often used to block them. When X-rays interact with matter, they collide with electrons. Sometimes the X-ray transfers all of its energy to the matter and gets absorbed. Other times, it only transfers some of its energy, and the rest is scattered. The frequency of these outcomes depends on how many electrons the X-rays are likely to hit. Collisions are more likely if a material is dense, or if it's made of elements with higher atomic numbers, which means more electrons. Bones are dense and full of calcium, which has a relatively high atomic number, so they absorb X-rays pretty well. Soft tissue, on the other hand, isn't as dense and contains mostly lower atomic number elements like carbon, hydrogen, and oxygen. So more of the X-rays penetrate tissues like lungs and muscles, darkening the film. These 2D pictures are only useful up to a point, though. When X-rays travel through the body, they can interact with many atoms along the path. What is recorded on the film reflects the sum of all those interactions. It's like trying to print 100 pages of a novel on a single sheet of paper. To see what's really going on, you would have to take X-ray views from many angles around the body and use them to construct an internal image. And that's something doctors do all the time in a procedure called a CT, computed tomography scan, another Nobel Prize-winning invention. Think of CT like this. With just one X-ray, you might be able to see the density change due to a solid tumor in a patient, but you wouldn't know how deep it is beneath the surface. However, if you take X-rays from multiple angles, you should be able to find the tumor's position and shape. A CT scanner works by sending a fan or cone of X-rays through a patient to an array of detectors. The X-ray beam is rotated around the patient and often also moved down the patient's body, with the X-ray source tracing a spiral trajectory. Spiral CT scans produce data that can be processed into cross-sections detailed enough to spot anatomical features, tumors, blood clots, and infections. CT scans can even detect heart disease and cavities in mummies buried thousands of years ago. So what began as Röntgen's happy accident has become a medical marvel. Hospitals and clinics now conduct over 100 million scans each year worldwide to treat diseases and save lives.
Você já teve que fazer uma tomografia? Bom, se ainda não fez, provavelmente um dia vai precisar fazer. Afinal, esse exame de imagem é usado para muitos diagnósticos. Quer saber como ele funciona? É o que a gente vai te explicar agora. A tomografia computadorizada é hoje um dos principais exames radiológicos. Capaz de detectar alterações muito pequenas em ossos, tecidos e órgãos, ela ajuda a investigar nódulos, tumores e até vasos pulmonares e cerebrais.
Ele pode ser usado para qualquer região do corpo, mas ele é particularmente útil na região do tórax, na região dos pulmões, para o coração, para avaliação de coronárias, e ele é bastante útil também para estudo do abdômen e da pelve.
Após o pedido do médico, o preparo do exame é simples. Basta estar em jejum, já que pode ser necessário o uso de contraste. Para as mulheres é essencial ter certeza de que não está grávida, hein? Tudo pronto? Então vamos começar.
O posicionamento é feito de forma simples, ele só vai precisar ficar deitado, imóvel. Durante a aquisição das imagens ele tem que prender a respiração, na maioria dos estudos, encher o peito de ar e segurar, para que as imagens sejam feitas sem artefatos de movimento.
Mas como funciona a tomografia? Bom, essa máquina trabalha lançando uma quantidade controlada de raio-x. Eles são liberados de um lado, atravessam o corpo e são captados do outro lado. Parte dessa radiação consegue atravessar tecidos do corpo e chegar aos receptores, mas órgãos mais densos, como ossos, barram essa passagem. É como uma espécie de sombra, e para captar imagens de diversos ângulos, ela gira ao redor do paciente.
A radiação de um exame tomográfico ela é muito pequena e ela tem caído absurdamente. Hoje em dia os equipamentos fazem, por exemplo, um estudo com 1/10 de radiação do que um exame de tomografia de 5, 6 anos atrás.
A duração do exame depende da área do corpo a ser averiguada. Exames de crânio ou de coluna chegam a durar até 5 minutos. Aí é só esperar o resultado, que deve ser analisado por seu médico. E se você gostou desse vídeo, não deixe de curtir e compartilhar com seus amigos. Quer saber mais sobre exames de imagem? Acesse minhavida.com.br.